Okay, let's try to do some stuffs. I switched iPads, so I don't have the work I did on this one last time. So we'll just start it over again. I'm just trying to think of something random I could say that would shock everybody and get their attention.
That's my brain.
Well, get your brain here. Do what? Yeah, we're not allowed to throw things anymore. It's not the 1970s. Still, if it's in the general, if you throw something in the general direction of a student, it's just no. The problem is like if I faked like passing out and dying, people would actually think it's too real because look at me. If anyone in the room is going to have a heart attack, it's going to be me. Can you whistle loud? Can anyone whistle loud? There we go. Okay, so we're going to start this problem over again because the other works on my other iPad. Yes. Yes. It's at home because during the week when the network was down, my old iPad didn't have the programming on it to be able to cast to other machines, and new iPads do have that ability. So I was like, okay, well, we're not going to have this again. So I would stick to paper and pencil, but I got to do this. I miss chalkboards. In particular, because I used to buy this chalk from Japan that was really, really smooth.
Then like write on it and then get a picture of those
Well. All right, so let's see. We have Q1, Q2, Q3. Let's put these on an XY axis.
I already have all.
I know. Okay, so they're positive, Q3 is a negative, positive, positive, negative. All right. Too bad. We'll put Q2 about there. And then Q3. And then we'll just go ahead and put points A and B. Big dog or little dog? You want a purse dog. Oh, okay. I was like, I don't know what a chi-chi is. All right. So let's find the potential at A. So this distance, okay, what are our distances? Okay, so that's 1 centimeter. So that makes that 2 centimeters.
So it gets up to well, now it's just it is
All right, so what do we need? So we have R3A. R1A. Because we'll do that in a,
These are them exactly.
okay. Beans is actually a good name for a cat.
He's so cute.
She is. She's a.
That's why I like that meme where the cat's feet are stretched out to a fire and it said baked beans.
We didn't know if it was a male or female, so we gave it a gender neutral name.
That's a pretty good idea.
Now we know. Sometimes it's complicated.
Well, as my grandfather used to tell me, you could always tell if it's a male or female by looking at the bottom of its feet. Think about it.
Business.
I thought the pre-vet people would have got that quicker. Oh, my grandpa used to tell me you could tell if an animal's male or female by looking at the bottom of its feet. That's okay. All right, so we have a couple of triangles here. Okay, what is, so Q2. So that's also 1 centimeter. Nope. All right, so we need to find these distances between the charges and point A. Don't fall for the trap on that one. I'm calling that 1 centimeter. That's actually the square root of 2. What about? Let's see, R3A. All right, so we have all our distances. And then, of course, our potential.
Oh, this is good. And then we have to do the whole thing again.
Mm-hmm. See, that's kind of why I'm doing it again. I was at the end of class and I know people were already going, I just want to leave. So, yeah, some people did. Did I? I don't see how it's the same notes.
No, this is a different. Like point B. It's like part B, but it's considered.
Oh, we have to, yeah, we'll have to change our lines for part B for the second part.
It's.
Mm-hmm. And so then, when you put all your numbers in here, make sure for Q3 you put in the negative sign. joules per coulomb, or volts? Oh, darn it. That's because I skipped part one.
So this,
Yep, this is part two. Yeah, this is part B. It was on a different page. Well, you already have part A from last time. And so
this one.
so I'll just go ahead and write this down. That's what we solved last time. We got that. So now we need the potential at A so that we can get the difference between the two. Let's see. Is that what we're doing? What does it say? Oh, work done. Okay. So all the solution you have from last time was for the first part of this where we solved the potential at B. Now we have to get the potential at A so we can get the work done. Okay, so we have both of our potentials that we need. And do you still have the reasoning for the equation for the work done by the field?
Wait, the equation.
Work done by the field.
This negative potential.
So it's negative potential. So we can do that. And then we have 6. Minus. And then our potential at B. So the work done, which way is it moving? From point A, the work done as the charge moves from point A to point B is negative joules. Again, because it's a positive charge, you're moving it from a region of higher positive charge over to where the negative charge is predominant. Yeah, so the negative charge. Yep.
So if you get the positive, then it's gonna be-
Yep. So you can think of that like if you have a positive charge and you're pushing it towards the positive dominant region, it's like you're pushing it uphill. So you have to, yes, you have to put work in. All righty. Potential due to a spherical conductor. We're just going to imagine that's a sphere. Well, that's not quite in the center, is it? That'll work. So we have a positive charge at the center of the sphere. So what's going to happen is the electric field is going to be transferred to the surface of the sphere. This is a conducting material. So the charges inside the conducting material are going to rearrange themselves and transfer this charge in the electric field to the outer surface. And so then everywhere inside the conducting surface, but also then imagine you have some field point out here at a distance r.
Is this the portion of the test sensitive?
Kind of. That was the E equals 0. The electric field everywhere inside of a conducting material is 0. Because again, think of it like a metal. All of the electrons in the metal are going to rearrange themselves to be positive on one side, negative on the other, and then transfer the electric field to the outer surface. So they had a whole list of those. Was it it wasn't Board Panda. Board Panda is a meme site. But anyway, they had a whole list of these. Just people who forgot to turn things in, who forgot to change their work before they turned it in. Some of them I couldn't post, or I would get Title IX and lose my job. So the things some people turned in was amazing. Like there was I won't tell you what she turned in, but she submitted a file and she goes, "Oh my goodness, I did not know you could see the file name when I submitted it." It was an interesting file name, and she sent it right to her professor. I just like this one because I thought it was relevant. So the potential out at point P is going to be just the same as if you were measuring from the point charge itself. The potential on the surface will be just at the radius of the sphere. I want to see if you guys can solve this one. Does that mean from cheeseburger.com? There was a whole evolution to that site, cheeseburger.com. It started off as Icon has cheeseburger and it was just like all cat memes, but then it just expanded. Okay, well, apparently I thought I needed a lot of room.
No, I don't watch this stuff. It's on Paramount Plus, it's not.
I'm still telling you, if you haven't seen it, you need to watch the SpongeBob video set to the hip hop song, This Is Why I'm Hot. Somebody did a wonderful job with that.
Someone did, they're like laughs by Eminem, but they did Disney like people.
It's like
It's the whole song, but it's did like Disney.
it's such a serious song though.
I don't know.
Okay.
It's impressive. Like, thank God. Like, this guy's 80 hours of work. Spent, gave me 30 seconds of money. I had to watch the movie.
Well, what was that song on SpongeBob? Was it the fun song?
Yeah.
Is it Friends or Fun Song? Yeah, yeah, that's it.
So that's where, so you, so this later, I see you. Absolutely. What's the middle meter?
And what's the joule per coulomb?
Uh,
Volts. Mhm. So I wonder if you simplified this or if you did it the hard way.
that's it. I feel like there's only one way to do it, like the equation.
But there were equations from earlier in the chapter
Oh, man.
and from last chapter.
Well, I got a 10 to the 18 7. Oh, I'm very wrong. Oh. Yes.
So if we look at these two, volts equals E times R. So that means that maximum potential well, if you got the right answer, you didn't necessarily do it wrong. You could just made it easier on yourself.
I definitely.
Yeah.
Or kilovolts. Always remember, just because we're in chapter 17 doesn't mean chapter 16 ceases to exist. Wow.
Yeah.
Wow.
Coming after we did.
I just thought you were gonna do the one CPTV probably next time.
But that is super easy.
Kind of like a trick question.
No,
No. Yeah.
I'll put a trick question on your next exam. We'll look at the difference. As I've told many people when they come up to me and they say, well, my truth is, I'm like, that's not how facts work. And as a physicist, there are objective truths and I can prove it mathematically. So, so just saying, I choose not to believe it won't keep you from getting shocked or electrocuted.
No.
Yep, you can do it later. So in a uniform electric field, your potential is going to be potential energy divided by Q. So you're going to get negative E delta R. Again, for potential, here's your volts, your joules per coulomb, your Newton meter per coulomb. Your electric field, your newtons per coulomb is also volts per meter. So this comes from the work of the electric field. We have our dot product. And then of course, for a positive charge, which is the way we do most of these problems, or most of the derivations, your positive charge has a field going out. And then the electric field is, so that if a positive charge with a positive charge, the force is in the same direction. Yeah, so theta 0 is 1. So we get Fe delta R, and our electric force is Q E delta R. To kind of like to graphically represent that. So a positive point charge in an electric field so then the change in our potential energy is negative the work done by the electric field, negative Q E delta R. And so then our definition of voltage we have a couple of definitions here. We're going to make sure you understand what electrostatic equilibrium is, and that the potential everywhere inside of a conducting material is the same. E equals 0 inside of a conducting material. Okay, so we have now we're back to conservation of energy. So again, it's written this way because and in an electric field, we have no non-conservative forces. So that means zero. And so you can work, so your deltas are final minus initial, and you can work out and get to this form of the conservation of energy.
I got it.
What show?
What if these parents all allow their kids to watch such an educational show?
Kids won't be allowed to-
Maybe the way, yeah.
Yeah, that's why it's.
Also-
Noise. I can just-
When I was a kid, it was Pee-wee's Playhouse. Watch that show if you ever want an acid trip.
What?
But one part was stupid, and one part was annoying when I
It's
was.
because she never really sat down and actually enjoyed watching. She thought great shit. Yeah, I know they must be-
Just, you know, what the water walking.
like, Monty.
A lot of barbecue. A lot of hand Montana. I was little.
So SpongeBob was too bad for you to watch, but they let you watch the morally degrading Disney Channel.
I was. Right.
Ah,
All of us very high noise tolerance. No, yes, very low, and everything was her, once I opened the bag of chips and she yelled.
well. Now, look at where I place these charges. Are these charges in the position of high potential or low potential? They're in the position of high potential because the positive is close to the positive plate, the negative is close to the negative plate. So then the forces on these I watched Looney Tunes growing up. Watch some old Looney Tunes. There's some dark jokes in there. Oh yeah. Like you could not play Looney Tunes on television today. All righty. Let's look at this. A proton is accelerated from rest through the funny thing, I showed this to Bruss. I said, I know it's funny. I just don't know why. Because I don't know the biology. Yeah, just allele uneven is what it said.
Is that a real pill?
Yeah,
What?
I'm pretty sure they are because I've been instructed on what real goats are. So, proton accelerated from rest through a potential difference. Its final speed is 2.0 times 10 to the 6 meters per second. What is the potential difference? And you get the mass of the proton. How do you think you're going to start this? Yeah, we'll get it set up because we're almost out of time from handing out assignments and whatnot.
Only know they find it.
We did this because then we can say so this is going to end up giving us the initial kinetic energy minus the change in potential energy. And then, of course, we know that potential energy no, that's not equals minus Q delta V. So then from here, delta V is going to be K final. Negative K final over Q. Where'd Q initial go? Where'd K initial go?
0.
Right. Remember, your kinetic energies are 1/2. And this time it's the mass of a proton, V initial squared. And you see how it says from rest. V initial squared is 0. So this whole thing is 0. Okay, so we'll finish this next time and try to finish up the chapter, because the next, you guys will actually like the end of this chapter because capacitance is some of the easiest math you're going to do. Well, it's like multiply this number by this number.
Oh, the price,